Okay, so 27 in 15.2. So the directions just say evaluate the line integral for dr. So we've started introducing sort of nicer ways to approach line integrals, but that's not what they're looking for here, right? They're just, you want to just do it with brute force and sort of the ugly approach. And so in this case, the f is cosine of pi x, and then what's it, yz, or no, zy, so that's your f, and then your parameterization, your curve, is given by x equals t squared, y equals t, z equals 2t, and then so then t ranges from 0 to 1/2. Okay. So let's go through this. So so again, no fancy techniques or anything, right? We're just doing sort of brute force here. So your r is just t squared t 2t, right? And so your formula is just f with that r plugged in and then dotted with r prime, right? So this is just f t dotted with r prime of t dt. And so, and I guess, well, I just leave it as c. Then you change your bounds here, right? So the bounds are going to be 0 to 1/2. What's f of rt? Well, you just plug t squared in for x, t for y, and 2t for z, right? So that just becomes
Cosine. T squared well.
2t t, and then r prime is just 1, 2. Okay. And then dot product. And we're taking the dot product of those guys, and so we end up with the integral from 0 to 1/2 of 2t cosine pi t squared plus 2t plus 2t, good. So 4t there, so let's just 0 to 1/2 2t cosine of pi t squared. I'm going to just break them up. Right, so that first or second one's easy, right? T squared or 2t squared should be your integral. Is that okay? So 2t squared 1/2 and 0. So if you plug 1/2 in, you'll get 1/4, so 2 over 4, so 1/2. And then you plug 0 and you'll get 0. So that's gone. This integral, what do you get there? So you could do u equals pi t squared, right? du is 2 pi t dt. And so maybe I'm just going to jump to the answer. So if you do that u substitution, right, you have the 2t out front, you don't have the pi, so you're going to get a 1 over pi cosine of u, and the integral of cosine of u is sine of u, right? So you're going to have 1 over pi sine of pi t squared, and then 0 1/2. Oops. So I'll just keep that as one line. And then it becomes, so plug in your 1/2, so you get 1 over pi sine of.
We don't have to change our form.
Well, no, because I went back to t, right?
Oh.
I made the substitution just, if you wanted to do it that way, you could do it that way. But I just left it with the t. So 1 over pi, I'll just write out sine of pi over 4, right? Minus sine of 0, so that's 0. And then plus, what do we say, 1/2 there?
Yep.
And then sine of pi over 4 is?
1 over square root of 2.
1 over square root of 2, so it's 1 over square root of 2 pi plus 1/2. So you gotta leave it like that. Root 2, right, this is also square root of 2 over 2 pi. And so if we wanted a common denominator, we could just do pi. Clean it up, you can get that. It looks a little nicer, but it's no more correct than the first one. Is that okay?
Yeah, I just forgot there is a pi there, I need to put it 1 over.
Oh, this piece here? Yeah. Easy mistake to make. Okay, and then the other one was 59? Okay. So 59, they give you f here. Well, they say f is the gradient of little f, and they give you little f, right? So little f. So z is 1 over x squared plus y squared plus z squared. And then c is defined by the vector valued function here, can't be t minus 1, 2t, 3t, and they say find the work done by the force field capital F acting on a particle moving along the curve. And so again, maybe that sounds intimidating on the surface, but the work we said was exactly what this formula was, right? It was really the reason why we said these are interesting formulas to look at this f dot dr. And so we're basically going to just do the same thing. We just need to do some work first. So what is capital F? Well, it's the gradient of little f. So that's f sub x, f sub y, f sub z. And if you get one of them right, the other one should be easy. What's
Minus 2x over x squared plus y squared plus z squared squared.
very good. Everybody see that?
Yep, and others just change x to.
I'm going to be super lazy. We get that, right?
Here.
Okay. So, and then I guess as long as we're over here, let's write out our prime. So our prime is just 1, 2, 3, right? All right. So then we want to complete this integral. So just like before, I got bounds, well, half of r dotted with r prime. Okay. So let's just plug those in. 0 to 2 is it?
Minus 2t plus 1.
Did I not write down the
0
bounds?
to 2.
It was 0 to 2? I don't trust you, that's why I'm walking over here. You were right. Okay. So 0 to 2. And then just fill these in, and again, I haven't done this one, so I don't know how ugly that is, but you're just plugging in the t minus 1 for x, right? 2t and 3t for y, and so they're going into our f, and so it becomes what, negative 2 times t minus 1 over, well, let's just write it out, t minus 1 squared plus
4t squared plus 9t squared.
and all of that squared, right?
Yeah.
Every denominator is going to be exactly the same, so I guess we're hoping some nice stuff will happen here. Let's just play it out and see.
4t.
What is it? Minus
4t.
2y, so minus 4t
All the same.
over. I'm just going to write that again, and then minus 6t
Yep.
over the same thing. And then we dot that with, was it just 1, 2, 3? So the biggest thing is clean up that denominator and see what it looks like. So let's just do that off to the side. So t minus 1 squared plus 4t squared plus 9t squared, right? So it's t squared
T squared.
minus 2t plus 1.
14.
Oh, you already had it, so, okay.
14 t squared.
14t squared minus 2t, okay, 0, 2, 2. And so now we dot this all together, right? And so every one of them is going to be over that same 14t squared minus 2t plus 1 squared, is that okay? And then what's that numerator? So it'll be 1 times this, so it'll be negative 2t plus 2, right? Plus 2, which will be minus 8t minus 18t dt. Okay. Minus 28
plus 2.
minus 28 plus 2 over. Okay. And so, right, you have a giant mess there, but you just hope that it turned out it was nice. And usually, when they put these together, they make them so they come out in a reasonable way, and this one does, right? You can let u be that denominator, 14t squared minus 2, and then your du is, well, there's the 28t, right? Oh, sorry.
Plus 1.
Plus 1. And then there's your du is exactly, well, it's negative of what you want, right? So you end up getting here, I'll worry about the bounds in a second, you end up getting negative 1 du, right, over u squared, is that okay? And then your bounds shift to be what, 1? And then I guess you're plugging 2 in, so what do we got? 56 minus 4, so plus 1.
53.
53, is that okay? All right, so are we good from here, or is this still where you're okay? You figured out what was wrong? Yeah. Yeah, so it's a little messy. I don't know that I put that ugly of algebra on the test.
I just made a mistake for when I'm plugging their RT.
Yeah, I mean, that's why some of these, all right, it's pretty contrived that you actually got something that worked out perfect where you could do this integration. Now, theoretically, right, we know how to integrate every rational function using partial fractions, and so at least in theory we could always do this, but in practice, not so easy. But if you can set it up, you can always tackle it with